Friends. We're Group 2. My name is Matt Walls, and I'm the team leader. And so today we're going to talk about the conservation of energy.
This is Muhammad Al-Hamza.
Our principle we chose is the principle of the conservation of energy. This principle describes that the total energy of an isolated system remains constant and therefore it is neither created nor destroyed. It is difficult to prove in the real world because a system cannot be truly isolated. For our purposes in this project, we only took potential and kinetic energy into consideration.
For our experiment, we analyzed a pendulum to check the validity of the conservation of energy. We measured the height from where we released it to the point where the bob is at its lowest point in the period. Our approach was to tie a rope to a 12-pound steel ball and the other end to a rigid pole, or in our case, a tree. Then we pulled the steel ball up, keeping the rope taut, and measured the angle the rope made with respect to its rest position, which was 45 degrees, and the height we pulled it up to, which was 1.75 feet.
Go.
I came in like a wrecking ball. I never hit so hard in love. All I wanted.
So for our experiment, what we did is that we basically took the pendulum to an angle of 45 degrees and then we released it so it started swinging. At the same time, two members of our team had started to calculate time from releasing point, which is in our case number 1, to number 2 at the center, and to number 3 at the left side, back to number 2 and back to number 1 as well. We did that a few times so we got the average time so we can determine the velocity. Using the time from the experiment and the assumption that the pendulum traveled the same distance each period, we derived the following equation for displacement. The first derivative gives us the pendulum's velocity as a function of time. Using the conservation of energy equation, the velocity is predicted to be 10.6 feet per second. Using the derived equation, the velocity is 10.57 feet per second. By this, our prediction and data line up nicely, suggesting that conservation of energy is still valid. There are some possibilities for data inconsistencies, such as friction, nonlinear motion, air resistance, wind, and human reaction time.
For our real-world application, we found roller coasters to be a fantastic use of the conservation of energy. What you may not realize as you're cruising down the track at 60 miles per hour is that the coaster has no engine. The car is being pulled to the top of the first hill at the beginning of the ride, but after the coaster must complete the ride on its own. You aren't being propelled around the track by a motor or hitch. The conservation of potential energy to kinetic energy is what drives the roller coaster, and all the kinetic energy you need is present once the coaster descends. Thank you for watching our video about the conservation of energy and how it relates to the real world.